So, welcome to module 5, and in this module we will be talking about process and threads. These are the next most visible part of the operating system, that when you start executing a program you create a process. Just to give you a background of what we have covered in the previous modules, I have a program, say hello world.c. I compile it, it gives you an a.out. So, hello world.c is a program, a.out is an executable program. So, we may call hello world.c as a source program or a source code, and a.out as an executable code. The moment you say /a.out and press enter, then a process is created. So, a process is nothing but a program in execution. Now, there is a subtle distinction between process and another unit of execution, what we call as thread. Now, a process can be multi-threaded, in the sense that a process can have many units of execution. So, what do we mean by units of execution? I will give you an example, and one of the best examples that I could think of is the Microsoft Word. The Microsoft Word in its entirety can be treated as a process, can be looked at as a process. And when you look at the different functionalities that is done by Microsoft Word, there is a functionality that accepts the input text, there is another functionality which formats it, there is another functionality which basically draws red line for your spelling mistakes, there is another functionality which draws green line for your semantic or grammatical errors, and then there is another functionality which basically stores your program. So at least we could think of 5 different functionalities or 5 different functions that are part of this process, and it is not necessary that all these 5 functions are done by one single sequential code, and that gives us a notion of what we call as a multi-threaded program, where each one thread will be doing one of these functionalities. So, when you invoke Microsoft Word, then there are 5 different execution units that are in action. One unit will be accepting the test, one unit will be formatting the test, one unit will be drawing the red lines, one will be drawing the green lines, and another will be automatically saving it at regular intervals. Each one of this can be called as a thread. Now, so in essence, a thread is also a code in execution, right? A process is also a program in execution, thread is also a program in execution. So, what is the difference between process and thread? And this is extremely important for us to understand, even from an information security point of view, because many times the hacks or the leakage of information can happen because of improper sharing or not a very rule based sharing of data between these different units of execution, namely threads and processes. So, before going into the explanation of what is the difference between a process and thread, let me also give you a background of what we have covered in this information security series so far. So, in the information security 2 course, we have talked a lot about computer organization. So, many of you would have read 2 subjects in your curriculum. One is called computer architecture, another is called computer organization. Some university curriculums have this as computer architecture and organization. We need to make a distinction between what is computer architecture as a subject and what is computer organization as another subject. Now, the computer architecture basically tells you how hardware is designed, but computer organization basically tells you how the compiler and the operating system can actually use the hardware that is designed. So, the computer organization basically talks about the interface between your operating system, compiler, and the hardware, while the computer architecture basically talks about how you build that hardware to meet those functionalities. So, in the second course, we have talked a lot about computer organization. We have talked about memory management, we have talked about process management, we have also talked about interrupt management. So, in the memory management, we have talked about segmentation, we have also talked about virtual memory or paging. We have also taught you how to write interrupt service routine for one of the most common architecture, that is in practice the XHS architecture. I strongly suggest that you go back to the videos of the information security 2 course, which is available for free, and look at those modules, and if possible do those exercises. If you do those, then appreciation of what we are going to talk in this course will make a lot more sense. These videos are available free in YouTube, thanks to IIT Madras and the MOOC platform, and if you have problems in accessing that, please put a note in the discussion forum and we will be too glad to send you the link, right. So, with this as a background, and with an assumption that you will make an earnest attempt to go back and look at those videos, I am now going to the next part of this course, namely process and threads. Right. Now, what is a process? A process is a program in execution. A thread is also a program in execution. Now, what is like a process, which is actually a program with which executes one instruction after another, the thread also will execute one instruction after another. A process can create children, right. So, when you boot a Unix system, then there is what you call as the first process that comes up, and that process actually creates many more child processes. So, the process is like a tree. There is one process that comes into execution when the system is booted up, and there are many processes that are spawned. Spawned means created or forked. So, different names are used in the operating system parlance, and these are the processes that are the child processes. Like a process, the thread can also create children, and like process, if one thread is blocked, another thread can also run, but in some scenarios. So, a process is a program in execution, a thread is also a program in execution. So, that is, so whatever a process does during execution, the thread can also do, and that forms those 4 similarities that you see in the slide. But what is the difference? So, processes, so let me give the difference by an example, right. You take Microsoft PowerPoint and Microsoft Word. They share very less information, or many times they do not share any information. So, these two can be treated as 2 different processes. They are 2 different executable programs, and they execute, and many times they execute in isolation. But when you take the other example of a Microsoft Word, in which there are 5 different execution units running, then they share lot of information. For example, the thread that accepts input, the thread that formats the input, the thread that draws green lines for that input, the thread that draws red line for the input, and the thread that actually saves that input. Note that in all these 5 sentences I have used that word input. That essentially means that this input is being shared. So, a thread shares lot of information among itself, and they collectively try and do a single job, while the processes can be 2 different entities doing 2 different, totally different functionalities, and may not and need not share any information. This is at a functional level, but even when you look at an architectural level, threads can share many resources. For example, the 5 threads that we have talked about inside Microsoft Word, as an example, they can share the memory, they can share part of the stack, they can share the code segment, they can share the data segment, some part of the code segment, data segment, etc. But then they will have some part which will be executing their own code, and then they will have their own stack, and each one may not share the general purpose registers, because when they execute, but there is a lot amount of data that 5 threads actually share, while this is not the case when we look at 2 individual processes. So, the main difference between the process and the thread from the architecture perspective and also from the functional perspective is they share more, threads share more information, while processes do not share among themselves. And the second most important thing that you should look at is that these processes do 2 different functionalities, 2 different processes do 2 different functionalities, while threads actually work together to achieve one functionality. So, this is something that we need to keep in mind. Since a thread is a part of the process and it need not carry that much resources specifically allotted to it, a thread is called a lightweight process. Now, why do we need threads? So, there are many interesting things that we need to talk of here. Some of the things that I have already explained, and some of the things that we will see here. Now, a process can have multiple threads, and these threads share common data, but then they can work in isolation one after another. The threading can happen at 2 levels, one is at a user level, another is at a kernel level. Now, this particular slide, though I am talking about many things that we have covered previous slide through my lecture, I will now make a distinction between kernel level threading and user level threading, and that will explain you why we need threads and what are the advantages and disadvantages of having threads. Now the operating system actually works in two modes. One is the kernel or supervisor mode, another is the user mode. In the user mode, the operating system runs certain programs, and if a process is executing in the user mode, it has very less privileges than when the process that is working in the kernel or the supervisor mode. So now when we want to move from the user space to the kernel space, then what we do is a context switch in which a user level program is basically removed and a kernel level program is basically scheduled. Now the switch from a user mode to a kernel mode or a user mode to a supervisor mode will take lot more time. In the information security 2 course, we have basically given lot of real examples, and also there are exercises which you can hand code, which basically teaches you how we can do a context switch from a user mode to a kernel mode. There we were talking about privilege levels. An Intel or an AMD x86 processor works in 4 privilege levels: privilege 0, 1, 2 and 3, while the privilege level 0 or 0, 1 and 2 can be supervisor mode, while the 3 can be user mode. Now what it means to move from privilege level 3 to privilege level 0, 1, 2, we have covered that in great detail in the information security 2 course. I suggest that you go and look into it. Now why are we talking about kernel and user mode at this juncture? The point is, when I want to implement threads, there is 2 ways by which I could implement threads. One is called user level threading, another is called kernel level threading. What is user level threading? The threads are created by a user program. So we have pthreads, etc., and the way we can implement pthreads is that we could create it at a user level. We can also create threads at a kernel level. Now when I do it at a user level, then when I want to context switch from one thread to another, so the threads do some multiple functionalities. When I want to do a context switch between the threads, I need not go to the kernel level. I can context switch at the user level itself. So the context switching actually becomes fast when working with threads at the user level. Why it is fast? Because when I do a context switch at a user level, since I share lot of memory, lot of information that are required with respect to memory need not be saved. You may have to go and save your program counter, your stack pointer and some general purpose registers, but you need not save lot of things about the address space. So for me to move from one thread to another is going to be much simpler for me and much faster for me when I use thread at the user level threading. But when I am doing it at the user level, one of the major disadvantages that you should keep in mind is that the kernel actually sees only one process, but the process could have multiple threads. Since these threads are created at the user level, the kernel will not know that I have 5 threads. The kernel will only see one process. So even if one of my thread wants to execute a system call, then basically it calls the kernel. The kernel will see that that request is coming from the process, not from an individual thread. So it will go and stall or suspend the process for executing the system call. So what happens is, if I have user level threading, and if one of my thread wants to execute a system call, namely it wants to write to a disk or read from a disk, then all the other threads will be suspended by the kernel. So the advantage of user level threading is context switching will be fast, but the disadvantage is if one of the threads has to do a system call, then every other thread will be stalled by the operating system. The other part is the kernel level threading, where the threads are created at the kernel level. When that is happening, then if one of the threads wants to do a system call, the kernel will know that this is the thread which needs the system call, and it will suspend only that thread. The remaining threads can still execute. But when I want to do switch from one thread to another thread, so I have to basically go to the kernel level and then do the context switching. So the context switching becomes slower when I do kernel level threading. So the slide why threads, this slide basically assumes that we are trying to do a user level threading, and many of these points become an advantage when you are doing a user level threading, especially the 7th point here which says that context switching are fast when working with threads. This is true when we do a user level threading, but this is not so true when we do a kernel level threading. Nevertheless, switching from one thread to another, whether it is user level threading or kernel level threading, is faster than switching from one process to another process. So, let me just sum up what I have talked so far. Yes, threads, the biggest advantage of having threads over multiple processes, you can say that I have 5 different functionalities. Why don't I create 5 different processes? Why should I create 5 different threads? The first thing is context switching is very inexpensive. I have explained that in great detail, and I also suggest, again I repeat, that go back to information security 2 course and see how really a context switching can happen in the context of a process. You will understand how difficult and expensive it is. Then the next thing is that sharing is also very important. Threads can share lot of resources, and there is a need to share these resources, as I had given an example of the Microsoft Windows platform. The disadvantage, as I have told you, blocking is a disadvantage. If I am doing kernel level threading, blocking is not going to be there. What do we mean by blocking? If one of the thread wants to execute a system call, other threads are also blocked, and this will happen at the user level threading, but if I do a kernel level threading, then this blocking will not be an issue. But again, whatever advantage that we talked of in the previous slide in terms of faster context switching will get a little bit degraded when we go to the kernel level threading. But why are we talking about threads and processes here? There is a big implication of security, because now I have different entities trying to share a resource. When an entity is shared, there is an extensive sharing, actually not a simple sharing, then there is a potential problem of security. We will address this as we go through not just information security 3, but 4 and 5 and the 5 courses that we have planned in this series. Lot of points will come out where the security is basically compromised because 2 processes or 2 units of execution, namely threads, are trying to share some information in which one of the thread can be a malicious one or can be a weak one which can leak information. So, this is where security gets compromised. So, if you want to actually become a good security engineer, you have to be very thorough with these fundamental things like what is thread, what is process, what it is involving. You need to have thorough knowledge of that, and that is what this course is aiming at. And so, please have undivided attention in the rest of this module and understand this. And again I repeat, I will be repeating it many times, please go through information security 2 course at the least. If you do information security 1 and 2, the videos if you look and come to this course, it will be extremely fruitful, but at least 2 you need to look at, so that you get the full effective delivery of this course from an understanding perspective. Thank you. Next, now we will go on to what kind of benefit an application get about threading. So, we will just see some examples of this. There is a proxy server is a very interesting example of a multi-threaded process. So, in general, if there are programs that has to do more than one task at a time, that will certainly benefit from multitasking. And so, the example again I have quoted here is the Microsoft Word type of program. But if there are sequential processes that cannot be divided into parallel tasks, right, then these are the things that will not benefit out of threading, right. So, one of the interesting thing is that as and when the processor, the architecture, the hardware started supporting multi-threading, now there is a onus or responsibility of everyone, starting from a teacher who teaches a BTech course, a student who learns undergraduate fellow, a postgraduate fellow, then he or she becomes a teacher. So, there is a generation responsibility that we have to guide the next generation in looking at concurrency, in looking at parallelism, how to see if there are components of your problem that could be solved concurrently, and that is very important. Unfortunately, today many curriculums do not address this issue. Hopefully, over a period of time, curriculums do improve and start looking at concurrent programming as a paradigm, even at an introductory stage, even at your first year of your undergraduate program or your postgraduate program. Concurrency should be taught, how to look at things as different units of execution that could execute in parallel, and if unless you do that, you will not use the full potential of modern machines. Today you cannot get a single core say excites this machine. You cannot get a single core machine on your desktop. Even your mobile phone will go up to 8 processors. So what will you do with these things, right? Just having processors cannot be a doll, right? You can't just keep playing. You have to use it. It cannot be just a showcase doll. So it's very, very important that all of us learn concurrent programming. If there are teachers who are listening to me now, if there are decision makers, university, board of academic courses, people who are looking at it, please, please, please go and start looking at introducing concurrent programming in your curriculum, and that is very, very, very important. And if there are people who are not looking from this and you know people who can make these decisions, please pass this video to them. Now I'll just summarize what do you mean by a context switch. Again, we have covered this in Information Security 2 course. So there is something called a process control block, a PCB. Now it basically saves information about a process, and what is that information that you need to save? We need to save that information so that at any point of time I can restart that process exactly at the point where it left. And when I am restarting, the entire state of the system, what do you mean by state? The program counter, the general purpose registers, the memory, the stack pointer, etc. should be restored at exactly the point I left. In addition, so we have to store the process state. What do you mean by process state? The program counter, the PC, and the process state is also whether when at the time of context switch, why did I context switch? We will see as we go into the scheduling in the next couple of modules. I context switch just because I made a mistake as a process, right? So that means I landed up in a trap. I say I executed divide by 0, or I did a segment overflow, or I wanted to actually take some help from the operating system. I want to print on the screen, printf or scanf. I want to read from the keyboard. I want to write or read out from a file. So I did a system call. So in these type of things, I go into a suspended state, and the operating system will finish the interrupt service or the system call and then get back. So my state would be a suspended state or a waiting state, after which I will go to a ready state and I will come back. So a process can be in different state. We will talk about those states very shortly. So we have to store the process state, then we have to store the program counter. I hope all of you know what program counters mean. Then the values of the different registers, then the CPU scheduling information, the memory management information like the page table, etc., and the possible accounting information for this process, how much CPU time I had used, etc., and then IO status information. So all these things constitute comprise what we mean as a process control block, and this needs to be saved so that the process can be restarted at any point from exactly the point where they left. So when we have multiple processes that are running, then each process will have a process control block, and these process control blocks will be maintained by the operating system, and as and when process 1 switches to process 2, the context of process 1 is saved in its process control block, and the context of process 2 is loaded from its process control block, and process 2 executes. Now process 2 finishes, and again or process 2 is pulled out and process 1 has to now execute. Then again process 2's context is stored in its process control block. Process 1's context is loaded back from its process control block into the system, and it starts executing. So the process control blocks basically maintain the context of all the processes that are currently executing. If you are having difficulty in understanding what I have told in this slide, please again go back to Information Security 2 course, and there we have explained everything in great detail. Now like processes, we could have thread libraries, and let us now talk about, there are two primary ways as you see, a library entirely in the user space and library at the kernel level which is supported by user. Now what is a thread library? Like math library, where you have lot of math functions already implemented, like cos, hyperbolic, I can do it in C, right? So similarly a thread library also will have several things which can basically invoke lot of thread related functionalities. We will see a very simple program down the line which will talk about different functions in this thread library. Nevertheless, when I want to use a math function, I say hash include math.h, and then I can use all the math function. Similarly, I can use hash include thread.h, and I can use several functions which are related to creation, termination and spawning of threads. Okay, so this is one of the very important thread library is the pthreads. This can be supported at the user level or kernel level, and there is a standard called the POSIX standard from IEEE, which basically gives you the application programmer interface for threading, thread creation and synchronization. So what is the application program interface? It actually specifies the behavior of the thread library, and this is common in Unix operating system, Solaris, Linux, Mac OS X. You can basically use pthreads there. Like how I could create a process and I could kill a process, or I can terminate a process, I can also do a thread cancellation. I can terminate a thread, and the thread can normally it can finish by itself, but it can also be killed. You could have asynchronous cancellation, which means it will terminate the target thread immediately. You could have a deferred cancellation, allows the target thread to periodically check if it should be cancelled, right. The thread can itself go and check for itself. So what is the main thing here? What is the role of the operating system? When a thread is cancelled, then it should immediately, the resources that are allocated to the thread should be brought back. But then there are multiple threads that are sharing that information. See, if a process is terminated, then all the information related to the process can be released. But in the case of thread, it cannot be. If I am having a user level threading and one thread terminates, then there are, or even if I have a kernel level threading, one thread terminates, what is it that I could get out of that thread? That's very important. What is it that I need to release? And if I fail to release, then it becomes a leak, right, because then it becomes nobody's resource. So when a thread is saying it is completed or it is cancelled, then we need to retrieve the resources, release the resources exactly pertaining to it, and that is going to be a problem, because I really don't know which are the information that is used exclusively by the thread and which are the information that are shared. So that is also one very important implementation within the operating system, because if I am not going to release it properly, then potentially I could have a leak of the resource, and I could also have certain security vulnerabilities there. So thread cancellation is very important, right. So to create a thread is like making friendship, but to cancel a thread is something like to maintain it. So it is very difficult to maintain friendship, and similarly a thread cancellation also is very difficult, much difficult than creating the thread. One of the very interesting things that have come up is thread pools, where these are lot of threads are already created and they are all awaiting work, for example a printer spool, etc. Right. So since I have created the work already, so there are some examples that have been given at the end, Win32 API and Java 1.5, where you can basically use these thread pools. So since these threads are created already, the creation is faster. So if you want to have a request, for example, I have a pool of threads which will do certain functionality, and I want to do that functionality, it is very quickly achieved by using one of the thread that is already created. Just I have to give some inputs or a signal, and it will work, and it will basically give back the result. So thread pools become extremely important in the context of real-time operating systems, where we are looking at very quick response time. We have talked about what are real-time operating systems and their distinction in the previous modules, and one of the things that we said that we are looking at response time. We need very quick response time, and these thread pools can be used for getting very good response time. And we could have thread specific data, and for every thread, each thread can have its own copy of data, and this is done because then it is useful when you do not have control over the thread creation process. So when I have a thread pool, so somebody requests for the thread, they take the thread, they execute it and get back. So I don't control that. As an operating system, we have less control over that. Now the moment I have thread specific data, now it is very important that when the thread completes, the entire data needs to get erased. The entire trace may have to go off, otherwise there could be a security vulnerability. So though threads are very interesting for us, threads need to be handled very carefully in the context of information security. Now this is a simple example of a pthread, and what we see there is that so two things are very important. First thing is there is a pthread.h, as I told you, math.h, we also have pthread.h. Then we can create a thread by using pthread t, you can get a task ID for this. Now there are two functions, we will not go into the entire pthread creation function, but let us look at two functions there, pthread create and pthread join. So basically the create will create the task ID, and there you also have, so when I create a thread, that means I say go, this is a thread, in this thread execute this program. Now what is the program that I am going to execute there? The program is called runner. So I am just looking at the fourth thing, pthread create TID, and you please note that there is a runner there. That runner essentially means another program, you see some program there down for runner. So I can create a thread and say in that thread this particular code will be executed, that is possible, and then I can go and exit from a thread. You see pthread exit inside runner, essentially it will exit. So this is a very simple example, I am not going into full details of what pthreads actually do, but this is an example where we say that threads could be created and the threads could be completed. We have talked about process state in some of the previous slide. So whatever process or thread, they have state. So a thread can be running, that is currently executing, or thread can be waiting to getting executed, so that is called a ready state, and the thread could be in a blocked state where it is asking for some system service, or it is asking, it is doing an IO, so it will be waiting, it will be blocked till that IO is completed, it will be blocked. After the IO finishes, it will be brought to the ready state, and then it will be scheduled for running. So running, ready and blocked are three states of a thread. We will cover that in using a state diagram in the next slide. Now so what happens is, first a thread, when you create, you call spawn. Spawn means you create a thread. Now immediately when you spawn, then it will go into a queue called ready queue. A queue will basically have all the fellows who can execute. Now a scheduler, if you are, it is a user level threading, then a user level scheduler will run. If it is a kernel level threading, and the kernel level scheduler will run, and the scheduler will know of all the threads that are waiting, it will find out whom should I execute, it will take it and put it into the CPU, then it will start executing. That time the thread is in the running state. Currently it was in the ready state, then it becomes into a running state. When it is running, it says it wants to do a printf, so immediately it calls the operating system. So now the operating system starts executing. At this point it will take that state, that thread, and put it into a blocked state, and it will do that scanf for that thing, and it will give the input of got out of scanf to that thread. Till now the thread is in block state. Once the system call corresponding to the thread is completed, then it is now again moved back to the ready state, again it goes to the running state. So this goes on, this merry-go-round goes one after another till the thread is completed. And then block and unblock are basically things. Block is to actually block that thread from running, so that because it needs some service. So what does block do? It actually does a context switch from the thread to a kernel level routine. So in the case of a block, then you actually save all the user registers, program counter and stack pointer, you save the context of the thread and move to the context of the service routine, and once the service routine finishes, you unblock that process and throw it back to the running ready state, and when all your things are finished, then you can come out of this. So this is a thread state diagram. When I spawn, I go to the ready state, and when I am scheduled, I go to the running state, and for some reason due to an interrupt, if I am preempted, that is stopped, I do not do any mistake, I do not want any service, but an external interrupt has come and it says stop, that is called preempt, then again I go back to the ready queue, and again the scheduler actually schedules me back, I come back to running, again I go back, if there is a preempt, back to the ready queue. So that are the two edges between ready and running state. But when I am in a running state and I ask for some service system call, I essentially get suspended, I go into the suspended state, or what you call as a waiting state. And when the call is serviced by the operating system and it is over, then I can go back to the resume state. Even when I am in a ready state, I told about user level threading, all my threads can be suspended if one of my threads want. So one of my thread is running, the remaining 4 threads, so let us say 5 threads are part of a process, so 4 threads are waiting, they are in the ready queue, 1 thread is running, and this thread now says I want to have a system call, then the remaining 4 threads also should be suspended, because operating system only knows one kernel. So this basically goes back, and then we go to the suspended state, and again when that system call is over, I resume, and at any state I terminate. If there is a need for termination, it is a user terminates or for some other reason gets terminated, the thread is actually deleted. So this is the thread state diagram. This will also be the process state diagram. In some sense we will look at process state diagrams when we look at the scheduling in the next thing. So with this we end this module. I hope you all understood more about threads and processes and the differences between them. The intention of this course is not to teach what processes are, that is done in the information security 2 course. Now we just give you a difference between processes and threads, right. So we will move on to the next module. Thank you.